So the last topic we're going to do with electricity and magnetism is the idea of electric fields and magnetic fields, and how to draw the field lines around either a grouping of charges or a set of bar magnets. So the first idea then, if we're going to talk about electric fields, so an electric field is a sketch of the pathways a proton would follow if you dropped it into the field. Okay, now that uses the word field in the definition of field, which is a linguistic and logical fault. So we'll maybe draw a picture and then it'll make more sense. Proton would follow if you dropped it into the field. Okay, so smiley face, what? Okay, so what I'm going to draw for you then is a positive charge here, and I'm going to draw a negative charge over here. Now you're going to have to think back to some of the previous stuff you've known about electricity and charges. The first thing is that like charges repel each other. So if I'm talking about dropping a proton around these two charged objects, the proton has a positive charge. It's going to be repulsed by this object. The second idea is that opposite charges attract each other. So not only will this test proton, the one I'm just going to drop into the field, not only will it be repelled by this charge, it will be attracted to this one. So there are no rules for this, and the answers you're going to get when you try the practice problems are approximate, because there's no way you could actually nail this without doing an enormous amount of math, which would involve vectors and maybe a touch of calculus. So we're just going to approximate the field by drawing some lines and see what we can get. So first off, I'm going to take the obvious path. If I put a proton anywhere between these two charges, right, on a line directly connecting them, it's going to be repelled by the proton and attracted to the positive charge and attracted to the negative charge. And it's going to just zip along that line. So I'm going to go a little bit over here. So on this side, that positive charge is going to repel that proton. But then as it gets further out here, it's going to be attracted into this one. So I might get a pathway that looks something like that. Right? Repelled by the positive charge and then dragged in by the negative. And on this side, it's going to do the same thing. And then if I drew one out here, I'd maybe be repelled by the proton, get a little bit out here, and then be attracted back to the electron. Same thing here. If I came out this side, I might do this. Out this side, it would be sort of symmetrical, and then out the top, something like that. And if I wanted to make it symmetrical, I could draw one more. So I get a mess like this. So if I were to take a particular proton, and I'm going to pick a spot on my picture, how about there? Great. If I dropped it at that particular spot, it's going to follow this field and end up there. That's the idea about field theory, is that there's this influence cast by these two charges. And if you put something that's affected by charge, like a proton or an electron or whatever, into that into the area of influence of these charges, it's going to move. And where is it going to move to? That's all these lines are showing you. So if you look at the diagram I've got, there's a few things that I need you to note about fields. So number one is, do you notice that the paths never cross? Okay, now the reason for that is very simple. It's that protons don't get to make choices. They don't have brains. They're just lumps of whatever they are. So if I were to draw in a hypothetical field line like this one, so that it crossed. Now imagine yourself a proton, and I put you here. Which one of those paths are you going to choose? Are you going to choose this one, or are you going to choose this one? Well, the question is flawed because, as mentioned earlier, protons don't have brains. They don't get to make choices. So the fact that this proton would be required to make a decision is why this line can't exist. There can only be one pathway at any particular point in space. So let me get rid of that terrible line there. Good. Number two. That's not green. Field lines come out of protons, or out of positive charges. And number three, they go into negatives. Methinks my green has finally bit the biscuit. Poor guy, he's been a brave soldier. All right. So the word that you might attach to this, for the fact that the field lines come out of it, is that a positive charge is a source for field lines, and a negative charge is a sink. So, I mean, matter is made up entirely of protons and electrons and some neutrons, but they don't care about electric fields. So, everything around you is either a source of electric fields or a sink for electric fields. And then all of the interesting things about chemistry are as a result of how these fields are drawn and how the electrons are able to move based on the paths that are available to them. You may have done some chemistry and talked about the s orbital and the p orbital and then the sp hybrid orbitals. Those orbitals are defined by the electric field surrounding those particular charges, and a little bit from the magnetic nature of bits. So these fields are fundamentally shaping the angles that atoms make inside of molecules, right? Like you may have drawn water, right? It's an O and then two H's up here, and they have a bend. Well, that angle is determined by the electric fields around those charged particles and around and from the magnetic fields that the electrons produce as they zip about. So, I mean, this idea is there's no math in this, which is going to make it feel a bit strange, because to be doing a physics problem without any calculations is just a little unusual. But buried in this, there is actually a great deal of mathematics and logic in the idea that you have to be able to draw these lines so that they never cross. It makes a pattern in space based on the idea of sources and sinks, and those three ideas together are going to determine everything about the physical universe that you've come across so far, or about matter anyway. All right, so I'm going to erase this one, and then we're going to try one that's a touch more complicated. Okay, So the difference between this diagram and the one before, notwithstanding that there are more bits, is that I have a charge here in the center that's more than one, right? It's 4 positive charges surrounded by 4 negative charges. So it's balanced, and I need to draw the pathways of these things, but I need somehow to show that there are more sources in this than there are sinks in any one of these things. So the way I'm going to accomplish that is that for every one line I draw connecting to a negative charge, I have to draw 4 from a positive. So let's make sure that that happens there. So the first path, because this was, and it says up there, where a test proton would go, here's an easy one. If I put the proton here, it's going to go straight into that negative. So I've drawn 1 into a negative, 1 into a positive. A path just like that, a path just like that, and a path just like that. Alright, so as you can see, each one of these negatives has a single line drawn into it, and the 4 positives have 4 lines coming out of it, so that the number of lines coming out of this is proportional to the number of charges that are in it. Another sort of trick when you're drawing field lines is you try and draw them all the way around the thing in a semi-symmetrical fashion. So there might be a charge that comes out like this, and then there'll be another field line that comes down like this, and then one that comes out like this, and one that comes out like this. And same thing, if I make this sort of symmetrical in all directions, there'd be one coming out like this, one coming out like this, one coming out like this, and like this. Alright. Now I'm going to look at this charge in the center. I have some vertical lines covered, right? There's lines coming out vertically, there are lines coming out horizontally, and there are lines coming out on all of the diagonals. So like north, south, east, west, and then northwest, northeast, southeast, southwest. So if I try and make sure that every particle is covered that way, so I can see where fields are coming from all directions, then I'm going to get a better picture of what this field looks like. So if I pick this particular electron, I have one in the southeast, the northeast, and the southwest. So I need one up in this corner. So I have to decide how I'm going to get up there. Well, I see a nice clear space here, right? A nice open pathway where I can connect. So I'm just going to do that. I'm going to grab a line from here. I'm going to bring it right in the top. And then I'm going to grab one. Well, I'm going to do that all the way around my diagram. So around and directly in the top. Around, directly in the bottom. Around, directly in the bottom. And so that covered my north. I have my north covered, my northeast covered. I want to cover my northwest. So I've got a pathway here that'll do that. Like so. Alright. Good. So I'm going to do that all the way around. Where was I going to? It's going to my... Okay. So I've got that covered. I need to cover my west here. Now, the only way I'm going to get a west line in there is if I can wedge it in between here. Okay, so I'm going to have to wedge one in here as well. And I'll have to wedge one in this teeny tiny space. And one in this teeny tiny space. Right, you see how this is getting more restrictive, right? It was really easy at first, but now that I have to get to certain places and I've already drawn all these lines and they are never allowed to cross, I start to have to be really careful about what I'm doing here. So this one, I need one on this quadrant here. So let's draw it in. There we go. And I need one on the south. Do I have that? I have north, northwest, east. I need south, and I have all four diagonals. So there's just one more left to draw into the south end here. So I end up with this, kind of looks like a flower. It's kind of nice. Diagram of what the electric field would look like for this particular object. Now, I'd like you to take a look at how that's been drawn. Do you notice that in this diagram, there are places where the field lines are very dense? Right? They're very dense here, and here, and here, and here. So that field has a lot of energy concentrated in that particular spot. It's allowed to, or it's able to what's the word I'm thinking of? Deliver a lot of energy to whatever my test particle is, because there's so many field lines in there. But out on the edges, right, they're much less dense, right? If I come out here, there's lots of space between all of these loops. So if I were to put my test proton anywhere in this sort of center area, it's going to move. And it's going to move very quickly and very directly to one of these four negatives. But if I put it out here, it's got a little bit of a curl to it. It meanders a little bit before eventually getting to where it's going. And so you can see by the density of the field lines, the intensity of the electric effect on any particular test particle. So, and you've maybe experienced this with static electricity in your house, right? If you've got a whole bunch of charge sitting on a window, right, glass picks up charge really well, or your hair or a balloon, the closer you get to that balloon with your hand, the more dense the field lines are around that charged object, and the more it starts to raise the hair on your hands. Okay, good. So this was a balanced one, right? There were 4 negatives for 4 positives. So I'm going to try and do one that's imbalanced, and then I think we're ready to try magnets. Okay, so in this particular example, I have 2 negatives and 1 positive. So it's not balanced. This object, whatever it is, has a net negative charge. Right? There's 1 more negative than there are positives. So this one, when I just start drawing the fields like I did in the last one, it's going to have some consequences as a result of that. So I'm going to do the easy one first, right? Straight out of the plus into the minus. Okay. And then there may be one coming out of here into there to cover my sort of northeast corner. And then there'll be one like this. Now you see I've created a teeny tiny problem here. I have 1, 2, 3, 4 lines coming out of the positive 3, and I only have 4 lines going into my negatives, but that's not enough. I'm supposed to have 3 coming out of this, 2 coming out of this, 2 coming out of that in multiples. So how am I gonna pull that off? Well, I'll need I'm gonna add 2 more so that this is 6 lines. Okay. There we go. So 1, 2, 3, 4, 5, 6 lines. So that's 2 per positive charge. So I'm going to need 2 per negative charge here. That would be a total of 4. And I only have 3. Well, you know, I could just draw another line and that would give me an extra one in here and that'd be okay. But I can't draw it from this. Because every one I draw out of here, I have to make another one into this. So I need a field line to come from somewhere else, like anywhere else, out in the universe, in order to complete the diagram of this. So I'm just going to draw it from here, like so, from the universe into that charge sink. And I'm going to need another one over here from this as well. So in it goes from the universe into my charge sink. Well, that's fine. So I'm going to keep drawing these. I'm going to draw 1, 2, 3 from my positive into my negatives. So there's 9 now. That's 3 per positive charge. I'm going to have to add 2 lines to this and 2 lines to that. Well, I got 1. I'm going to have to draw another one. And another one here. Alright. And then another 1, 2, 3. And then that was 1. Draw another negative 1 from the universe. Negative 1. So just to count them, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 4 lines per positive. So I should have 8 lines on this and 8 lines on this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You should be there. And 1, 2, 3, 4, 5, 6, 7, 8. There. Okay. So I'm going to add 3 more charge lines here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 5 per charge. So I should have 10 around this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. And 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I need another one here. 10. There we go. And if we do it again. 1, 2, what's another one here? 3. That should be 6 per charge. So I need 12 around this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That one's good. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I could keep sketching this, and that'd be good. I can keep doing it. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, I need 14 per charge. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so that's what my field's starting to look like. Now, I'd like you to take this diagram and I'd like you to zoom out. So if I zoom out real far so that I am drawing this instead, well, that's, yeah, that'll be fine. Do you notice that in and around this spot, right in here, there's like a whole bunch of, it's madness right in around here, right? All sorts of craziness happening right around these 3 objects. But then out in this end, there are field lines coming in like this. That should be pointing at the negatives. And eventually, when I start running out of space over here to try and connect them, these field lines are going to have to start wrapping in from the other direction. So I'm going to get some that do something crazy like this. They come from really far and then wing into those electrons. Or negative charges, sorry. Something like that. Now, if I zoom out even further, so that I'm drawing this, when I'm this far out, I'm not going to see the mess on the inside. I'm only going to see this arrangement of fields that are on the outside. So there'll be a field like this, field like this, like this, like this, like this, So as I zoom out far enough so that I'm not close enough to see all these little fine contours, eventually this diagram is going to look like a net negative charge, a single negative charge, where it's just field lines coming in forever into this central point. Now, at this point where I can still distinguish that it's two sets of negative charges and a positive, I might get more intensity on this side. And less intensity on that side because I have some masking. Right, this negative field is masked a little bit by the positive over there. If I were to zoom out even further so that it looked like this, I don't know, there's some charge there, like a single molecule of water that's had one electron stripped off, so that it's a teeny tiny object and it only has a very small charge differential, but I'm a very large object that can't see molecules or atoms arranged in things. That's going to end up looking just like a single naked negative charge with no real difference. Alright, so again, we're just sort of eyeballing this. So if you were able to draw something similar, like something like this, then that'll be good, right? As long as you've got an idea for how these field lines kind of work. All right, good. So I'm going to clear this off, and then we're going to try some magnetic field lines. Oh, wait. I want to add a fourth thing to this particular list. And in classic McDonald fashion, I'm going to put it on top of the list. Oh, let's renumber them. New number 1. Lines only go to infinity if the charges are unbalanced. So this line here, this line came from forever away. It came from infinity, right, out there. And so did this one, so did this one. And the only reason I was allowed to draw lines coming in like that was that I had an imbalance in my charges. So if that's number 1, that's number 2, this is number 3, this is number 4. There. We have a nice, complete list. Let's do one more. This time I'm going to imbalance it so that the positives are winning. All right. So lines only go to infinity if the charges are imbalanced. I look at this particular thing. I have 5 positive charges and I have 4 negative charges. So I'm going to have to draw some lines to infinity for this particular one. And I'm going to have to draw 1 going to infinity out of this positive for every 4 that I draw into my charges. So let's do that. So 1, 2, 3, 4, and 1 to infinity. All right, 1, 2, 3, 4, and 1 to infinity. 1, 2, 3, 4, and 1 to infinity. 1, 2, 3, 4, and 1 to infinity. And 1, 2, 3, 4, and 1 to infinity. All right, lovely. Now you can start seeing that this is starting to get plugged up. So eventually, if I were to do another 1, 2, 3, 4, I'm going to have to draw one out here eventually So keep in mind this is a proton, right? So if I put a proton here, it gets pushed away from that +5, and it's getting drawn into the -2, but I've run out of places to bring it in. So that proton gets attracted in, bent over, but it doesn't actually get pulled in. It just sort of escapes. Maybe another one like that over here eventually. And these are those field lines that are going to show the ever-expanding net positive charge as you zoom out on this thing. Lovely. Okay, so I'd like you to look at this particular spot here. Notice that I had to start crushing them in together because these two things are there. Notice that this has some symmetry to it along this axis, but it does not have symmetry along this axis. So these field lines are crushed in there. And a field is a physical object, right? It's not just an imaginary set of lines we draw on the board. You have this physical thing here that's been compressed. And like a spring, to a point, it doesn't like that. It wants to be symmetrical. It wants there to be less stress here and more stress there so that the whole thing is balanced. So if these three objects were able to move, you're going to try and see in your head that they would be happier if they were arranged in a line. Because if that happened, then I would have symmetry along this axis and along this axis. And that's sort of how nature likes to be, so that there isn't build up of energy in one place and not in another. It's that idea that nature abhors a vacuum, right? It wants everything to be uniformly filled. Because if you put energy in one place, it tries to flow to places where there isn't energy. All right, good. So on to magnets. All right. So if we're going to start drawing field lines for a magnet, we're going to have to modify this list a little bit. So number one, lines only go to infinity if the charges are unbalanced. So first off, it's not charges. Magnets don't have charges. Magnets have poles. So if the poles are unbalanced. Now here's a nasty little catch about magnets, is that you can't have an isolated north pole. You can't do that. Such a thing doesn't exist. And I think if you were a particle physicist, you might have an argument about that. But if you are working in a lab someday and you manage to isolate the magnetic monopole, right, the thing that is just north, imagine what you could do with that object. If I could make this marker purely North Pole, I would take it outside and I would let it go, and it would, on its own, with no energy source, just drag itself to the magnetic north of planet Earth, right? You'd have an object that would just move for no reason. It'd be able to gather energy out of that magnetic field. And then once they got there, that gathering of north there would start to neutralize the South Pole, like the magneticness of magnetic north, and eventually the Earth's magnetic field would fail, and then we'd all die from cancer from the radiation, background radiation, particle radiation from the giant ball of fusion going on nearby. So that'd be bad. Don't do that. You'd also be able to like paint like the bottom of you imagine like you paint the bottom of a chair in north poles, and then you paint the floor in north poles, and then that chair would just hover, right? Again, with no energy, it would just hover like that, and I mean, such a thing would be amazing, but would violate a whole bunch of other rules. So net, this idea here, lines only go to infinity if the poles are unbalanced. That will never occur. You'll have a north and a south, and they're always coupled together. So I'm gonna get rid of this. the paths never cross, that one holds, right? Because these things are supposed to be pathways for test magnets. So I can't have choices. Magnets, like protons, also don't have brains, right? They can't make choices. So there should be no field lines crossing. Field lines come out of positive sources. Well, that's not positive anymore. That's going to come out of north poles. And field lines go into south. And these two things apply outside of the magnet. Okay, so how do we resolve this? Well, if the paths aren't allowed to cross, the way I keep myself from drawing anything out to infinity and making sure they never cross is that I have to draw loops, right? So this idea of sources and sinks doesn't really apply to magnets because I'm drawing loops. I start from a north, I draw my loop back to the south, and then I finish the loop through the magnet. So I have a field like that. And I know I didn't draw anything to infinity because I had to close the loop. So just for symmetry, if I draw one like so, like that, and maybe another one up in the center, another one like here, and then maybe a little bit at the edge. Something like that. Now you notice in here my ends are too full now, so I'm going to get a few loops that escape the magnet a little bit and come back around. Escape the magnet and come back around. As long as I draw a full loop, then I'm okay. And there'll be another loop like this. Another one like this. Now, if you've ever played with magnets, you maybe have noticed that there's this weird spot in the center of them where if you try to push the two magnets together, they don't like to do it, and they will rotate around that center point, right? Like that's where it feels like there's a squishy object stuck between those magnets. Well, that's this place here where it transitions from north to south. So you've got your maximum density of field lines coming out at the north end of this bar and the maximum amount of field lines into it at the south end of this bar, and there's sort of a decreasing field out here. And you notice that none of them go to infinity. There are no sources because it's a complete loop. There are no sinks because it's a complete loop. And I've drawn them so the lines never cross. Alright, so I'm going to erase this and we're going to try one where we have a few magnets located together. Okay. So I'm going to try and draw some loops here. So I'm going to pick this place to start. Okay, it's a little bit on this edge. Now, this line here, this field has to get from the north to the nearest south pole that's available. So I think between the two of these, I'm not going to be able to get through here. I'm going to have to go around. And so if I try and do that, as I'm trying to get around to this south pole, I encounter this one. And so I'm going to get sucked into that. And then field lines go through the magnet, come out the north. Now I need to get from the north to the nearest south pole, and I also need to connect this loop. So maybe like this, and through the magnet. So I've got a field line there. If I try and draw that again, again. And then at some point, you see how long this path is getting in order to get from the north to the south? So at some point, it's going to be shorter to get from the north to the south over here. So we'll start drawing some of those. And over on this side, I'm going to have a couple that make it into the bar here like so. And then there's a few in here. You see I'm starting to get like these really dense fields in this area. So I'm not going to be able to draw this without making my paths cross. So eventually there'll be a few that don't close. They just go in there. And then on this side, there'll be some where, again, there's too many field lines here, so they're going to have to come around and do some of this action. All right, lovely. So, you know how hard that was to draw all those loops. And when I look at it, I see a bunch of them inside of this magnet, which is okay. I mean, a magnet's a magnet. It should have field lines in it. And I have a magnet there, which has a bunch of field lines in it, and that's okay. But I have this buildup of them there. And the universe doesn't like a buildup of energy. It likes it to be nice and uniform everywhere, a nice and symmetrical field. And this drawing is anything but symmetrical, right? Like that's a hot mess. So if I were to think about this, these fields here, they don't like to be like that. If I try and think of an orientation that would be a little bit tidier, these wouldn't be so dense if I didn't have these two things close to each other. Alternatively, I could get them inside of a magnet if I were to click the two ends together. So if I took this configuration and I tried drawing it like this, so those same two magnets, I'm not going to draw the top edge because it's going to run in here, but if I turn this one like so, then I'd end up with the field doing this. Which is nice and smooth, nice and spaced out. It would be symmetrical on the other side if I had room to draw it. This is a more balanced field diagram, and ultimately this silly picture is showing you why configuring magnets like this makes them move. Right? There's so much energy built up in that field that it is physically able to turn the magnet, either turn this one like this or turn this one this way, so that the field lines are a little more smooth. Okay, good. So I think I'm just going to leave you with the practice problems. You need to just try this. There are many options on the practice sheet for you to give a go at. You're going to try and draw them, and then you're going to look at what I drew, and you're going to remember that I am also approximating this field when I draw them. So when you take a guess, that's good. We're just trying to use this diagram to get an intuitive sense of how these fields would be drawn. There isn't a correct answer as long as you are following the rules. So give it a try, see how it goes.